Have a look up here. Let's talk about these three. I picked three kind of hard ones from the most recent free assignment. So what do we do? We're going to find all the complex solutions. So what do we got to do?
Move it all to one side.
Okay, move it all to one side. So we might as well make the leading term positive, right? So we'll get 768 x to the fifth minus 243x equals 0. Okay, that one.
You should probably pull like a 3x out of that.
Okay, so we could factor out. It looks like 3 goes into those. How do we know?
Yeah, 240 is 81. 768 is something.
Right, and you can tell by what's the trick again? Add them up, and if the sum of the digits is divisible by 3, then the number is good. So we could factor out a 3x, couldn't we? Well, not anymore. We made that one positive. So we got 3x. If we divide that away from each term, what's left behind? What? 259. Is that right? Boy, that's bad. That can't be right. What is that? 256. X to the fourth minus 81. Okay? So now what?
That's a sum of squares.
Not sum.
Difference.
Oh, difference. Okay. So now this one actually probably maybe wasn't the best example to pick in a way, because this one sort of has to be a difference of squares. But what if this had been something like, what if we had had something else? Like, what if we'd had a number times x to the sixth minus something else, right? Say we had a slightly different problem like we had last time, where we'd have an option of doing either pattern, either a difference of cubes or a difference of squares. Which one do we definitely want to use? Difference of squares, right? And just think about why. Think about the rationale. In order to remember that, think about why you're avoiding the difference of cubes pattern. Because if we're taking packets of something bigger than x over here, it's different. If we have something simple like if we had, say we had 1,000 x cubed minus 64. I mean, yeah, you could, I guess you could find a way to make that a difference of squares, but that obviously wants to be a difference of cubes, doesn't it? Right? This one is easy to do as a difference of cubes, though, because you only have x's in there. You don't have packets of anything bigger than that, and so when you get that ugly quadratic factor at the end, no big deal. It's just quadratic. It's just in packets of x, right? Like if we factored this, then I guess we could divide both sides by something too. Instead of a 64, we make that a 27. So we can't divide it anyway. So that's, what are the cubes that are being subtracted here? What's the first cube? Yeah, right? Cube root of 1,000 is 10. Cube root of x cubed is x. Second one?
3.
So then what's our pattern?
X minus 3.
Minus 3 times.
100x squared.
Good, so 10x squared, quantity squared. So 100x squared.
Plus 30x.
10x times 3, so 30x.
Plus 9.
Okay, that's fine, right? If we're trying to find the complex zeros, when we set these factors equal to 0, we get them. It's fine. We're going to get an easy answer with this one. And here we're just going to use the quadratic formula, right? We're going to get a complex conjugate pair. Imaginary, they have eyes in them, kind of like they go together as a conjugate pair. If we had something a little trickier than that, though, and let me think about how I'm going to do this here. So this could be, like, what if we had, thank you. What if we had 1,000 x to the sixth minus 64 equals 0. Okay, you see here's where you face kind of a crossroads. You could either, you got option A and option B, right? We could either turn this into a difference of cubes. We could write that as 10x squared cubed minus 4 cubed equals 0, or we could write it as a difference of squares. We could write it as, oh, 1,000's bad, isn't it? Oh, bad one. What I meant to say there instead was, what did I mean to say? What did I mean to say? Just make it an x to the 6th. We'll make it easy, right? So if it's x to the 6th minus 64, I could either break that down into difference of cubes, and x squared cubed minus a 4 cubed, right? Or I could break it down into difference of squares. I could make it x cubed squared minus 8 squared, right? Okay, you see the problem with doing the top one. If I were to break this apart into a difference of cubes, look what's going to happen. I'm going to get an a minus b, that's fine, times a squared plus ab plus b squared. That's terrible, right? That's terrible because it's quadratic, it doesn't factor, and you've got an x to the 4th there and an x squared, and that's really hard to deal with. So you absolutely do not, you don't want that, right? So we're not going to do it that way. We're going to break it up. We want to always, as much as we can, we want to always use the easy pattern, which is the difference of squares first, right? So we end up with a minus, that's just a 2 cubed, right?
Sure is.
So we get a minus b times a squared plus ab. What am I doing? Sorry. We're going to get a minus b times a plus b. Sorry. Right. A is x cubed, b is 8. Sorry. Right? Because we have a cubed, or a squared minus b squared there. So there's our a minus b times a plus b. Those are easy, right? Those are cube differences in sums of cubes, but it's just an x cubed. It's not an x to the 6th, so it makes it easy. That one we can do. You tell me, how many solutions?
6.
I'm going to get exactly 6 complex solutions. Now, it could be that there's going to be some multiple solutions. It might be like if I had something like x squared, I don't have it here, but if I had one solution was x squared equals 0, well, I get x equals 0. That counts as 2 though, right? Because I did it twice. It's x is being squared, right? Here I am going to get 6. And we can see that, can't we? Because when I do a difference of cubes, what happens? I'm going to get one linear solution, and I'm going to get 2 imaginary solutions every time. So from each of these, I'm going to get one real and 2 imaginary, 1 real and 2 imaginary for a total of 6. Right? Get the idea? Okay. So moral of the story, you want to do the difference of squares first, and then last step, if you need to, you'll do the sums and differences of cubes. But you want to really save those to the end if you possibly can.
So that was just completely random over there on the right? We haven't even touched the left one yet?
No, so left one. So what are the squares here? I can think of this as being
Number.
what squared minus what squared.
9. Second one. 9.
Second one is 9. First one is,
Third.
no,
16.
16
X.
x squared. There you go. Right? Square root of 256 is 16, and x squared is x to the 4th. So there's my a squared minus b squared, right? So out in front, I've got my 3x, and then what does this break up into? Well, I just get a plus b times a minus b, right? And those are easy. Those are quadratic. I can just isolate x. Subtract 9, divide by 16, square root. What are my answers? What are my zeros?
0,
0.
Probably.
I get x squared equals negative 9/16, right? If I subtract 9 and divide by 16. So if I square root both sides, what am I going to get? Plus or minus 3/4 I. There's 2. And then over here, if I add 9 and divide by 16, I get x squared equals positive 9/16. So plus or minus 3/4. So 1, 2, 3, 4, 5, which is what we expected.
Where's the 0? Oh, the
Because it's a
0 right
5th degree polynomial.
there. Here's 5.
Okay? So here are, just for the note purposes, there's our answers. Okay? How about, questions on that before we move on?
Let me write it down. Or he's gonna write the whole thing.
Well, I'll put these on notes immediately, so they'll go on to move.
We don't have time for that.
Well, it's faster than writing it down. I'll go back to it. I want to get through this. As we're done, I'll go back to that page for you. So what about finding all the complex solutions of this equation?
Okay. Move it all to one side.
Move it all to one side. So which side do we want to go to? Okay. So we're going to go to the left because we're going to get a positive number, the leading coefficient we want to be positive, leading term. So well, it doesn't matter. Yeah, I guess it would. So we add x to the 8th, we get 3x to the 8th, doesn't matter. We're going to add 2x to the 5th and get how many?
Oh, boy.
We're going to subtract 2x squared and get
600.
okay, there's our equation. Now what?
So we could get this?
Pull an
Yeah.
x squared,
Yeah.
pull a 3x squared.
Okay, we could pull a 3x squared out front, couldn't we? So we factor out a 3x squared.
Are you testing on this?
Yeah, we're going to test on this, yeah.
That's the most important.
So what's left behind if I factor out a 3x squared? From the first term I get x to the 6th. Second term,
21 x squared.
okay. 35 cubed, x cubed, good. Plus 216, okay. So that helps. Now we've got a trinomial in here, right? It's got 3 terms, and it looks pretty bad, but this fits our quadratic pattern, right? If we think of this white factor here as being in packets of what, it's going to look better. X cubed, right? If we think of this in packets of x cubed, that's like saying x cubed squared plus 35 x cubed plus 216.
You know what I'm gonna probably screw up there?
What's that?
I'm gonna probably cube root that 216 on accident. Like that'd be a common mistake. What?
Going from here to here?
Yeah.
Okay, so all we did here then, let me just point out what we did. Let me, up here, folks, up here. You gotta really get, I know there's a lot of stuff coming at you, but you got, if you can just get it, and this is the thing, going into college, best strategy in the world. Because you're gonna take hard math classes in college, all you guys will, I know you will. Your goal is to get it in class. If you can get it in class, it's easy to re-get it later, right? So you just wanna focus to where you can get it in class, and then you'll get there again. You know, I promise you, you'll get there again. If you get it one time, it comes back easily. So, what's our goal here, right? The goal is, this is the thing, this is the hardest thing to see, but you don't do anything to this term, why would you? All we're trying to do is put this into a quadratic form. Now, if you want to do this for a while, I promise you won't need to after a while, but make a variable substitution if you need to make this look normal, right? If we make this substitution, let's just say, instead of calling that an x cubed, because it looks kind of ugly, at least in your head you can do this, let's call it something like u. U is a real common, just you think that's weird that I pick U all the time. That's the most common variable to substitute for a function of x or expression involving x. We do it in calculus all the time. So if U equals x cubed, then what does that factor become? It becomes U squared plus 35U plus 216. That's a chapter 2 problem, right? You guys can factor that. That's just factoring a quadratic trinomial where a is equal to 1. We're just looking for magic numbers, aren't we? Right? So what are the magic numbers that multiply to 216 and add to 35? Oh boy, what are those?
13 and 12.
No.
27 and 9.
27 and 9, does that work?
No, it doesn't work.
That's
too much.
Well, we might have to.
18 and 7.
18 and 7, does that do it?
I don't know.
No,
No.
that is not good.
No, that's not it.
No, it's not, that's 100.
So we better figure it out. So
827.
8 and 27, is that it? Okay,
Yeah, 28 and 7.
there you go. If all else fails, make a factor tree or just make a list of factors of 21 and see which one, or 216 and see which ones work. So this breaks down into U plus 27 and U plus 8, right? Everybody agree? Okay, but we don't have to really call them U's. U's just x cubed, right? So that's the whole point of this, is to break it down into a pattern where we have something squared plus 35 times the same something plus 216, so we can factor it just like we did in chapter 2. Okay? So then this breaks down, this splits apart. Instead of a U, we've got x cubed plus 27 and plus 8, and then I've got my 3x squared out front. Now it's doable, right? Now we've got factors that we can, easily fit into patterns. This is a monomial factor, so we already know the 0 of that one is 0. Here we get a sum of cubes and a difference, or two sums of cubes. So we just follow the sum of cubes pattern for both of those, and we're done. Do we want to finish this?
No.
Okay. I mean, I don't. If you want to come see the rest of this, I want to get people going. Come up and I'll go through it with you individually. But from here, it's not a big deal to find the zeros, right? That's the tricky step in this one. Okay. Last one. Let's at least talk about the strategy. Okay. So what do we got?
Move it all to the right.
Move it all to the right. Excellent idea. So if we move everything to the right, what do we get on the right?
Why should we go to the right?
So we get positive number. It's not a huge deal. But so positive 32 x to the 5th. What about the x to the 4th? Actually, plus as I move it over there. Oh, look at this. Cancels. Okay, this isn't working for me right now. I want to get you going, but I know you're probably talking math, but I want your attention all up here. Talk through. If you have something to say it to the group. Contribute by all means.
Plus
108x squared.
And then plus 27x.
How do you do that?
Oh,
If I just add the 31x to the other side.
That's not good, right? That's the
Yeah, we did.
You're right. The 0 should have been on the left, but then I tweaked it.
Didn't that make it different though?
No,
So if you move it all to the left,
same thing. If I move it to the left and it distribute and multiply to -1, could do the same thing.
Like commutative property.
Exactly. There you go. Commutative property.
I think
Okay,
it's-
so
that's pretty different.
now we got 4 terms, right? So we know that if we've got 4 terms, that's not a trinomial pattern. We can't rely on the old tricks from Unit 2. We're going to have to use the grouping thing, aren't we? But before we do that, what do we always want to do first? Because there's a hang-up in this one. I made this hard. We want to pull out the greatest common factor, and I don't think there are any numbers we can take out, right? But we could take out an x.
right.
There's no common factor of all those coefficients, but I could pull an x out front. And what does that leave me with?
32x.
It's gonna be a multiple of
8x cubed.
x.
Okay, that's where, now we got to factor by grouping, don't we? If we've got 4 terms in this factor, the only way that we can deal with a 4-term factor is to group it, factor by grouping. So we got to go kind of remind ourselves how that works. So we've got our x out front, and then in the first group, what do we do? Good, take out a GCF, so we're going to take out an 8x cubed, and we got to figure out what's left over.
That's how you raise yourself back. Oh, you're splitting it in half.
So I get my 4x. Yeah, we're just splitting it down the middle. First 2 terms and last 2 terms, right? So 4x plus what? 1. Okay, here's a common mistake. Common mistake is if I'm factoring out an 8x cubed, a lot of times people will just, when they're in a rush, they'll write that as a 0, right? But I'm not subtracting it, I'm factoring it. I'm dividing each of these terms by 8x cubed to see what's left over, right? So 8x cubed divided by 8x cubed is 1, not 0, right? Okay, plus.
27.
Now, what do we know over here we have to have? We've got to have the same leftover. We've got to have the 4x plus 1. So the question is, can we make that work? What times 4x is 108x?
27.
Well, let's distribute it and see if that works. 27 times 1 is 27, so it does, right? So it does factor by grouping, and so we know this is going to work. So then we've got our x out front. We've got a common factor now from each of the two terms, right, that we've broken this up into. The first group of 2 became, when we factored it, became this 2-factor term. The second group of 2 terms became this 2-factor term, right? And the common factor is the 4x plus 1. I saw a hand.
That right.
Right.
So if you just did the right side, and then it was different than 4x plus 1, or there wasn't 4x plus 1,
Then, okay, yeah, so what if question, what if when we distributed this, I got something other than 27 and the answer is blows up, doesn't work, can't do it. Yeah, you couldn't solve this one by factoring by grouping. Now, I obviously probably gave you ones where it does work, but it won't always work. It's just a strategy for factoring that often works, but not all the time. So we could pull this 4x plus 1 out front, and then what's left behind? 8x cubed plus 27. And now this is very manageable, right? When we apply the zero product property, we can already see that we're going to get 0 and negative 1/4 pretty easily, right? Those are going to be our 2 simple linear factor solutions. And then here we've got a sum of cubes that we could break this down further.
You mean 0 out front.
So, right. So we're going to get a 0 is going to be one of our solutions coming from that guy, a negative 1/4 from that guy, and I'm going to get 3 from this one, 1 real and 2 imaginary in the form of a complex conjugate pair, right? Okay, go. Any questions, answers?
Did you edit? Delete your ear. It's like a TV show.